everybody. We're talking about extending the definition of exponents. If n is a positive integer, we know a to the n just means a times itself n times. And in the last video, we talked about if we're going to extend the definition to give meaning to a negative integer exponent, because it's not clear what it would mean to multiply a by itself a negative number of times. But what we decided is if we want that rule to remain true, then we have to define this as 1 over a to the n. So it would make sense to give it that meaning, because giving it this meaning ensures that this rule that defines how exponents make sense will continue to work. Okay, so by that same argument, let's today think about, well, let's not do it in general, let's look at this. So like 2 to the 1/3. What would it make sense that this one should mean? So I'm going to give a similar kind of an argument, but we're kind of going to step our way towards it. So hopefully it feels intuitive that I could extend this rule. Instead of just saying a to the b times a to the c, we could multiply it again, a to the d. And that should be, b plus c plus d. Again, assuming all of these exponents are positive integers. If they're all positive integers, the reason that makes sense is the following. This ridiculous string of multiplied a's here is supposed to depict b of these a's, because this is just saying a times itself b times. And then after I multiply b times, I multiply it by itself c more times, and then I multiply it by itself d times. And so if you ask how many times overall did I multiply a by itself, it must be b plus c plus d. And that's what's happening on the right-hand side here. So that's why it should be intuitive to extend this rule, assuming all of the exponents are positive integers. All right, so let's repeat the same kind of argument that we did last time. So if that rule is going to remain true, the question is, what meaning should we assign to that set of symbols, 2 to the 1/3? So what I'm going to do is I'm going to have 3 copies of these. And so if we assume that this rule is true, we can add the exponents to get 2 to the 1st power, or 2. So what we've described here is we've described a single number times itself 3 times equals 2. So let's call this m for mystery. So 2 to the 3rd is m. So we've got m times itself 3 times equals 2. Another way of saying that is m cubed is the same as 2. And so if I want to know what m should equal, the answer is cube root 2. But remember, m was just equal to 2 to the 1/3. So what we've done is we've said, if we want this pattern in exponents to remain true, even when the exponents aren't positive integers, we need to define 2 to the 1/3 to be equal to cube root of 2 in order to maintain that identity. Okay, let's make the same argument in general. So what if I wanted to assign a meaning to 2 to the 1/4? Well, I couldn't set it up the same way. I couldn't say 2 to the 1/4 times itself 3 times, or I could, but in that case we would end up having 2 to the 3/4. And we don't know how we want to define 2 to the 3/4. So we can't say we have something whose meaning is unclear and we're trying to figure out what it would make sense to assign it by saying this meaningless thing times itself 3 times is a different meaningless thing. So instead of doing it 3 times, I think it would make sense to do it 4 times. So if we had 2 to the 1/4 multiplied by itself 4 times, again, we know that the exponents should add together to give us 2 to the 1st power. And so now, if we say m is 2 to the 4th, we've got m times itself 4 times equaling 2. And so that means m should be the 4th root of 2. So hopefully you're starting to kind of see the pattern here and how we're going to make the argument. So we've done it for 2 to the 3rd power. We've done it for 2 to the 4th power. Let's do it for a to the 1 over n power. So the way the argument's going to go is I'm going to say, let's take this mystery thing. I'll define it as m. So let's take this mystery thing and let's multiply it by itself over and over and over again. How many times should we multiply it by itself? Let's do it n times. So if those same laws of exponential addition remain true, the exponents should add to be 1. And so we know that I've got m times itself n times. So instead of writing thing times thing times thing times thing, which is like m times m times m times m, I've just written m to the nth power equals a. Remember, I'm trying to figure out what meaning should m have. So if I take the nth root of both sides, I've got m is the nth root of a. So what we've discovered is, in order to keep these laws of exponentiation true, the meaning that a to the 1 over n should have is the nth root of a. This is not the only way you can make the argument, and if you look at the practice set, there's another way of making the same argument that some people might think is a little bit cleaner or a little bit nicer. But hopefully this idea makes sense, that we're not proving anything, but we're saying if we want certain patterns to remain true, you have to define this pattern in a certain way.